So when you take an unknown acid or base of unknown concentration, and then you add a known concentration of an acid or a base to it to determine what the concentration of the unknown is, we call that a titration. And we can monitor this reaction by seeing the change in pH. Because if we start with an acid, we know that the pH is going to be low. And as we keep adding base to it, we know the pH is going to eventually increase, and finally go through neutral, where the concentration of acid and base are the same, and then zoom up to a basic pH. And at that point, we want to know exactly when the concentration of the acid and the concentration of the base are the same, or the number of moles of acid and base are equal. So we call that a titration experiment. That's what we're going to be doing tonight. So the goal is to take some acetic acid, in other words, vinegar, and hopefully everyone has the vinegar that was included in the kit, and then some other random vinegar. I mean, everyone's got vinegar in their house, right? So they got like white wine vinegar or rice vinegar or grape vinegar. I mean, whatever they have. So use one should be the one that came with the kit, and then the other one can be any random vinegar in your house. So what we're going to do is, since we have a fairly good idea what the concentration of acetic acid should be, we can determine it exactly by adding a base of known concentration. And so we'll be able to calculate the molarity of the acetic acid in the vinegar. We'll be able to calculate the percent by mass of the acetic acid in the vinegar. And we're going to figure out what the pKa, which is the 1 to the minus log of the Ka. If you remember what the Ka was the dissociation constant of acetic acid. And since acetic acid is a weak acid, its Ka will be low. And so we can actually from this experiment figure out what it is. And then we're going to calculate the percent by mass of acetic acid in vinegar, because that's how it's sold. You should, at least for the vinegar that comes in the kit, you should get a percent by mass of around 5%, because that's how commercial vinegar is sold, by percent mass. So just a little background, we sort of talked about this in class the other night, but what we're going to be doing is titrating protons or hydrogen ions. We can look at them like this, or we can look at them like this. And we're going to be adding hydroxide ions. And we're going to be taking advantage of the fact that when we have H plus and OH minus in solution, they perform a neutralization reaction and form water. So what we're going to start with is an unknown concentration of protons, of H plus. And then we're going to add a known quantity of OH minus and follow that reaction by seeing what the pH changes is. So we know that the pH scale ranges from 0 to 14, 0 meaning it's completely acidic, 14 meaning it's completely basic. And then at pH 7 in the middle, that's where the concentration of H plus equals the concentration of OH minus. They're both the same. And when they're both the same, we have the pH is right in the middle between 0 and 14. So this is an equation we sort of learned the other day to figure out how we calculate pH. So it's really important you be able to use logarithms. Log 10 we're going to be using. because these are really small numbers we're dealing with. Both the concentrations of H plus and OH minus and the Ka of the acid are all really small numbers. And so it's much, much easier to talk about them as a minus log. And so that's what pH actually is. It's just the minus log of the proton concentration. So a titration is what we're going to be doing tonight. And so we're going to be using something called a titrant. A titrant is a solution of known composition and concentration. What is our titrant tonight?
Sodium hydroxide.
That's right. And what's the concentration we're going to be using?
1 molar.
1 molar. Excellent. Yeah, though for calculation's sake, let's just assume that it's 1.0 molar, because with 1 molar, we only get 1 significant digit. So let's at least go for 2, because I'm pretty sure the concentration, I mean, that is provided for titrations. So I don't know why they don't put 1.0 molar on it, because usually when a company provides a concentration of a strong acid or a base for titrations, it's usually to at least 2 significant digits and sometimes 3. Let's just use 2. We'll use 1.0 for the concentration of the sodium hydroxide. So since we're using sodium hydroxide, we're using base. If the titrant is a base, then the unknown solution is going to be an acid. And we call that the analyte because we're analyzing it. And generally, when we're doing this sort of experiment, we use something called a burette. That's a piece of glassware that is specifically designed to do titrations. So you can see here that it's a very long, slender tube that we fill up with our titrant. In this case, it would be our sodium hydroxide. And you can see that it's measured off in plus or minus 0.01 mil intervals. So we can measure the volume very accurately with one of these. And that's kind of the whole point. Anyone remember when we talked about our experiment last week, when we had something with TC and TD on top of the piece of glassware? Do you remember what the TC and the TD stood for? Remember, we were using all kinds of different glassware to measure the volumes of things. And at the top of the piece of glassware, it either said TD, it said TC/TD for most of them. For some, it just had TC. Nobody remembers. TC stood for to contain. Do you remember what TD stands for?
To deliver, right?
To deliver, exactly. So notice that the burette only has TD on it. It is designed specifically to deliver a precise amount of liquid. And how it does it is we turn this stopcock here, made of silicone. You turn it and you can actually add like less than a drop at a time. You can add like a quarter drop or a half drop, like really, really small volumes. Because as you'll notice tonight, when you're doing this reaction, when you get close to what we call the equivalence point, you're going to want to add really, really, really small volumes of sodium hydroxide, because the reaction, it goes like that once you get really, really close to the point where the base then is a higher concentration than the acid. And we want to get as close to that point as we possibly can. So this is what the reaction actually is. We take acetic acid and sodium hydroxide. And the sodium hydroxide is such a strong base, it actually pulls this proton directly off of the acetic acid, leaving us with sodium acetate and water. So which one is the conjugate base in this reaction? If the acid is acetic acid, what's our conjugate base?
Sodium acetate.
That's right. Man, you're crushing it tonight. Yeah, sodium acetate. Sodium acetate is a fairly strong base but it is complexed with sodium for a little while, and then that dissipates. And then we're going to have this base and then additional base. And so the pH is going to go up once all of the weak acid is gone. So we'll have a dramatic change in pH. So let's have a look and see what that looks like. So this is what, if you were looking at the pH during a titration. So here's the pH over here, and this is the volume of sodium hydroxide you're adding. So you add, this would be 25 mils of acetic acid. And notice that the pH, when you start out, is around 3. It's because acetic acid isn't a strong acid. It's a weak acid. So the pH is going to be a little bit higher than if it was a strong acid. And then the pH will change. It'll go up, but only slightly as we're adding more and more NaOH. You see it goes from 3 up to 5, up to 6. And then when you get the same when the number of moles of acid and base are the same, that's called the equivalence point. That's when you have moles of acid equal moles of base. So right here for acetic acid. Notice that the equivalence point isn't at pH 7. And that's because our conjugate base is acetate ion. And as I mentioned, acetate ion is a relatively strong base. And so it increases the pH. So the pH, if you had a strong acid and a strong base, the equivalence would be at exactly pH 7 because the conjugate acid and base there are both weak. In this case, we have a strong conjugate base, so the pH is a little bit higher. So what we want is something to indicate that we've reached the equivalence point, because we're not going to be recording the pH. We don't have an electronic pH meter to look and see what the pH is. If I was in the lab, that's the way I would do it, and I have a robot do this. But we're doing it with a syringe and some vinegar. So what we want is an indicator that tells us we've reached the equivalence point. And since the equivalence point is slightly basic, we want an indicator that indicates that we've reached a slightly basic pH. And so that's why we're going to be using an indicator called phenolphthalein. The pKa of that indicator is 9. So around pH 9, it changes color. It goes from clear and it turns pink. So what you're going to notice when you're doing this reaction is when you're going to add, we're going to take our acetic acid, we're going to add some of the pH indicator to it, the phenolphthalein, like 2 drops is really all you need. And then when you add some base to it, you'll notice where the base drops into the solution, it'll get a pink color. And then when you swirl it, it disappears. and you'll add a drop of base. It'll turn pink around that drop, swirl it, it'll disappear. So what you want to do is get as close to this point as possible and not go jetting past it. So the end point is where we estimate the equivalence point is. It's basically impossible to get to the equivalence point because you would need to add exactly the right amount of sodium hydroxide to exactly equal the concentration of acetic acid. And that's basically impossible to do. You're going to go a little bit past. And when you go, because when we go a little bit past, that's where you get the big pH change. And so we're going to estimate to get as close to this equivalence point as we possibly can. So what we want is a pale pink color. If we get this bright red color, that means we have gone way past. That means we're like over here somewhere, like a pH 11 or pH 12. We want the pH in the solution to be around 9, 10 at the very most. But if we get up to 11 or 12 or 13, that means we've gone way past the end point. Oh, figure this out. So the other thing not only we're going to be using that information to calculate what the concentration of the acetic acid is. Because if we know what the concentration of the hydroxide ion, and we know the volume of the hydroxide ion, we know moles of hydroxide ion. And we know in this instance, moles of hydroxide ion will equal moles of H+, which will equal moles of acetic acid. But the other thing we can also calculate is the Ka. We can calculate the Ka by seeing how much volume of the base it took to titrate the acid. And it may not appear how we're going to do that immediately, but remember that Ka is equal to the concentration of H+ multiplied by the concentration of the acetate ion divided by the concentration of the acid. And if we rearrange that equation, we get this. The pH of our solution equals the pKa of the whatever the acid is, plus the log of the acetate of the conjugate base, in this instance acetate, divided by the concentration of the acid. Notice it's not the concentration of H+, but the concentration of the weak acid. Now, if we think about this, the pKa will equal the pH when the concentration of the acetate ion and the concentration of the acetic acid are the same. Because when they're the same, when we divide them, that equals 1, and the log of 1 is 0. And so if we can estimate where the concentration of acetate ion and the concentration of the acid are the same, and we know what the pH is, that tells us what our pKa is. And for all intents and purposes, that takes place midway through the titration. Let me show you. So at the beginning of the titration, we have all weak acid and very, very little acetate. The concentration of acid at the beginning is way more than the concentration of the acetate because it's a weak acid. We make very little of the acetate. Now, at the end of the titration, all of the acetic acid is gone, and it's all been turned into acetate. So at the beginning of the titration, it's all acid and no conjugate base. At the end of the titration, it's all conjugate base and no acid. But right in the middle, halfway through, so if the beginning is 0 mils of base added, and the end of the titration is 25, well, at 12.5, we have titrated exactly half of the HA. We have turned half of the HA into acetate ion. So if half of the acetic acid is now acetate, that means the concentration of both of them must be the same. And that's where we can use the pH at that point is equal to the pKa. And if you look at this particular titration, you can see that the pKa of acetic acid, or the pH midway through the titration, is a little less than 5. It's around 4.9. And if you look up the pKa for acetic acid, it is around 4.9. So you can use this equation to help us figure out not only what the concentration of the acid is we're titrating, but if it's a weak acid, we can figure out what its pKa is as well. So any questions about this? Oh, I do want to point out this is a misspelling. It's the Henderson-Hasselbalch equation, not the Hassel-Balch equation. I don't know who Hassel-Balch is. I know that's kind of a lot to go through, but one of the questions on the report is calculating pKa. So I just wanted to make sure you had some familiarity with this. So do we understand how midway through the titration, the amount of acid and the amount of conjugate base, since we're halfway through converting all of it, they should equal each other. And when they equal each other, this particular part of the equation, when A minus and HA are the same concentration, that's log of 1, and that is 0, because 10 to the 0 equals 1. So basically we can eliminate that, and at this point pH equals pKa. And when you look up the pKa for acetic acid, you'll see it's a little less than 5. So that's an accurate determination. Any questions? What's the score of the ball game? It's the 3rd inning last I checked.
Still 0.
What are they, in the 5th by now? All right. So this is what we're going to need. So you need a 10 mil graduated cylinder. That's what we're going to measure our acetic acid with, or our vinegar. We need a little Erlenmeyer flask, a plastic cup, balance, a 10 mil syringe, since we can't give burettes to everybody, although I really don't know why. I guess if you have a burette, you need a stand to put it in. So sending you a plastic burette wouldn't have been a problem, but getting you a stand to put it in so it's perfectly up and down might have been an issue. And some vinegar is actually included in the kit. So notice you're going to need a sheet of white paper, and I'll explain why you're going to need that, and your own vinegar sample. Like I said, white wine vinegar, rice vinegar, grape vinegar, whatever the vinegar is. You probably don't want to use red wine vinegar for reasons that will become obvious. So from chemical kit number 2, the phenolphthalein indicator, which is basically impossible to spell. I mean, I've been using this stuff for like 40 years. I still don't know how to spell it. And the sodium hydroxide. And like I said, it really should be 1.0 molar. So we're going to treat it like it is 1.0 molar, just for our calculations, okay? So what do we do? So we take our 10 mil graduated cylinder and put it on the balance, and then dispense about 5 mils of vinegar into the cylinder using a transfer pipette. Then we're going to record the exact mass of the vinegar. This way we'll be able to get a precise volume. And not only that, we'll be able to figure out the percent mass of acetic acid. Because remember, we should get about 5% acetic acid by mass. So put 2 drops. So transfer that volume to the Erlenmeyer. Take 2 drops of phenolphthalein and drop them in to the vinegar. That is the start point of the titration, where there is no hydroxide added. And then take a little picture so you can see what the color is. And then we're going to transfer 10 mils sodium hydroxide to the small cup and then use that to fill our syringe. We don't want to have any air in the syringe. Be really careful with the sodium hydroxide. Like I said, that will not only burn your skin, it will dissolve it. So really make sure you got your goggles on. You might want to wear gloves as well. So what we're going to do is record the initial volume of the syringe to the nearest 0.1 mils. Like if you don't get it to exactly 10, don't worry. Like if you start with a volume of like 9.7, or in this instance, like, 0.3, that'll be your starting volume. And then whatever you finish your volume at, let's say you finish at 4.1 mils, just take the difference, and that'll be the volume of sodium hydroxide you added. So place the flask with your vinegar on a white sheet of paper. Now, that's really important to do, because since we're looking at something going from clear to pink, it's really hard to see against a dark background. So if you get, just some white paper or something and put that underneath, it makes seeing the color change much easier. And then we're going to add sodium hydroxide in 0.5 mil increments. So just really gently put like, 0.5 mil, swirl, 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 then another 0.5 mil, swirl, swirl, swirl. And we're going to keep doing that until the color change persists for a little while. Because you'll notice at first, when you put the hydroxide in, 1 or 2 swirls and it disappears. But as you get closer and closer to the end point of the titration, the pH is going to be higher and higher and higher. And so when you swirl it, it'll take longer and longer and longer for that color to go away. Basically, what we're looking for is this at the end. This is a perfect titration. So that is like extremely pale pink. That's perfect. I mean, you'll be lucky to get that, because you're going to do the titration several times. You do it like 3 times. But that's what you're looking for, that color right there. This one has gone over, not too much, but it's clearly gone over. And this one has gone way over. So if the color is that brightly colored pink, then you've way overshot. And so your calculation of concentration is going to be way off. So what you want is to get as close to this as possible. And if you get this bright, bright, bright color, basically just toss that out and do it again, because this will not give you a good result. This will give you an excellent result. This one will give you a pretty good result, but that last one will give you a crappy result. And that's why we want you to take the picture, because basically it'll show us how careful you were doing the titration, and that will affect your grade. So if your titrations all look like this, you know, we want you to do this well, and doing it well means getting right up to the equivalence point and then just going barely past it. So once you're swirling and it takes a couple seconds for it to go, then we start adding drop by drop, just a little bit at a time, hopefully to get that pretty pink color. Yes, you want to keep going until a single drop of sodium hydroxide causes that color change that persists for a little while. And you swirl and swirl and swirl, and maybe that bright color goes away, but the pink color doesn't go away entirely. That's perfect, because you've got the pH to be around 9. And that's what we want the pH to be. So once you've reached the end point, take another picture, and that goes into your report as well. So then record the total amount of sodium hydroxide required to reach the end point, put that in the data table, dispose of that, rinse the flask, and then we're going to do another 2. Okay, and then calculate the concentration based on your experimental data. This is what the molar mass of acetic acid is. It'll tell you what the concentration of acetic acid will be. So here's an example. So I've got 10 grams of an HCl solution, so hydrochloric acid solution, and I titrate it to the end with 6.2 mils of a 1 molar NaOH sample. So I've got 6.2 mils of sodium hydroxide, and it's 1.0 molar. So that's 6.2 mils times 1 liter over 1,000 mils times 1 mole over 1 liter. So that gives me 0.062, 0 moles sodium hydroxide. So the concentration of hydrochloric acid is going to be the same, or the amount of moles of hydrochloric acid is going to be the same. And this shouldn't say grams of HCl, it should say mils. That's a misprint as well. So that tells us, so the amount of moles of HCl is the same, because there's 1 mole of sodium hydroxide for every 1 mole of HCl. Remember, when we did the workshop on Tuesday, always balance the equation before you do these calculations to make sure that it's a 1-to-1 ratio of acid to base, or it's a 2-to-1, or it's a 3-to-1, or whatever it is. We know with sodium hydroxide and HCl, it's 1-to-1. So that tells me how many moles of HCl I have. Now, I multiply that by, I want moles over liters for concentration, right? And I have 10 mils and I want liters. 1 over 10 mils. There we go. 1,000 mils over 1 liter. And so I multiply this by 1,000. I actually multiply this by by 100. 1, 2. So my final concentration is 0.62 molar. So that's how you would do a titration, calculate the number of moles of the acid, figure of the base, figure out how many moles of acid that is. What's the volume of your of the base? What's the volume of your acid? And then you figure out the concentration. Once you know the number of moles and you know the liters, then it's a simple matter of figuring out moles per liter. All right, so this is what our first data table is going to look like. So remember, we're recording the mass of vinegar. And then we're going to be, so record the mass of vinegar on the balance. This is what the density of vinegar is. So then we can convert that to volume. Here's what your syringe said before you started adding it, what the syringe said after you had finished adding it. Figure out what the volume of the sodium hydroxide you delivered. You know the concentration is 1.0 molar, so it'll be pretty easy to determine the moles delivered. Then you have the moles of acetic acid, the mass of acetic acid, figure out the molarity, and then calculate the percent mass of acetic acid in the vinegar, knowing that the molar mass, I believe, is around 60 grams per mole. And like I said, you should get around 5% approximately. That's for the known vinegar. And then you're going to do the same thing for your unknown sample. And then the third data table is basically figuring out what the pKa is. So the pKa of acetic acid is 4.7. The volume for this particular titration. So this is data they've given you, and you try and figure out what you calculate the pKa to be. So you should get around 4.8 or so. If you have some questions on how to do this, we can discuss it. But basically, they're giving you data from a titration that somebody else did, and you basically have to figure out what they tell you what the initial volume was. They tell you what the pH was midway through, and you have to figure out based on that what the pKa is. So you need to figure out what the moles of acetic acid are halfway through, what the moles of acetate ion are halfway through, and then use that equation, the Henderson-Hasselbalch equation, to figure out what the pKa of the acid is. Okay. So got to have some questions after all that nonsense. Anyone have any questions before we get started? Oh, apple cider vinegar. Is it red?
Oh,
A little? Yeah, that might be problematic because as we see, we're looking for a red color. So if it's already red, that might be hard. That's why I recommend you don't use red wine vinegar. I mean, you can try it, but yeah, that might be a little problematic. I think you want something clear. I mean, if all you've got is just another, plain vinegar, just use that, right? So we're going to be doing 6 titrations, 3 with the vinegar sample that was given, and then 3 with your whatever sample you want. You can try the apple cider vinegar. I'm not sure you'll be able to see the color change. Anyway, everyone want like 5 minutes to get all their stuff together and their goggles on and all their gear together, and so at 8 we'll get started. How's that? All right.
Good.
And we can check the score of the game. Right. So cameras on, please, if you can.
Professor, I have a question.
Can we use something like rice vinegar? It's a little bit yellowish.
Yeah, that should be fine.
Okay.
Yeah, it probably won't affect the pink color, but I mean, you'll see if you have trouble seeing it, you'll notice.
Professor, I have a question.
Yep.
My syringe came like this. Would this still be usable for the project? It's missing this portion.
Wow. Oh wait, that's the big syringe. You want the 10 mil syringe. That looks like the 25 mil
This is
syringe.
It came broken. Would this still be usable? Or would the measurements be different because it's missing that portion?
Actually, I don't think it'll matter that much. As long as it doesn't leak out the bottom.
Okay.
If it leaks out the bottom, then yeah, that won't work. But if it doesn't, then I think you're fine.
Okay.
But that's a 10 mil syringe, really?
Yeah. If you see right here, it says 10.
Oh, okay. Yeah, I guess you were like, yeah, when you hold it so close, it looks huge. Oh my God, it's huge.
Yeah.
All right. So let's see what they're.
And then, Professor, I have another question. So for
Yep.
measuring 0.5, the tick marks, are they going by, like, for example, 2?
Yes,
Like-
you want to be halfway. So there's 5 tick marks for every mil.
Uh-huh.
So half would be 2.5. Yeah, basically it doesn't really matter
Okay.
whether it's 0.4, 0.6. What really matters is when you get close to the equivalence point, that you start going drop by drop. That's really the part that's important.
Gotcha.
So if you add a little bit more, a little bit less at first, that'll be fine. Oops, I got grains here. That doesn't help. The hell do I get grains? Grams, there we go. Wow, so 11 grams right on the nose. Now you should have a transfer pipette, like one of these. This is what you want to transfer the vinegar to the graduated cylinder. And then when you get to around 5, you can just 5 mils, you can just stop. And if you go a little bit over, that's no problem. What's most important is you get an accurate mass. So I've gone a little bit over, but doesn't really matter. 5.79 grams. So then I'm going to use the density to convert that to an accurate volume. So here is my cute little flask, and I'll transfer all of that in there. Now notice that I had some water in here already, but I am not concerned. Why is it not a problem if I dilute this now? I can add water to this and it will not affect the reaction. Why is that? I could add another 5 mils of water to this. It would make no difference at all. How come? What are we actually titrating? Are we titrating the volume? What amount of acetic acid are we actually titrating here? What's the unit? Somebody help me. What's the unit of acetic acid we're titrating? It's not volume. When is my titration over? When something equals something else. What is it that equals? What are the two things that have to equal each other?
Molar concentration.
Nope. I can use whatever molar concentration of sodium hydroxide I want. Makes no difference. So it's not concentration. Is it volume? With my volume of base equals volume of acid? Is that when the titration's over? What is it? But two things equal each other at the end of the titration. Something between moles. Whoop. I gave it away. It's moles. It's when moles of acid equal moles of base. So if I dilute this with water, remember, I don't change the number of moles. Remember, when we dilute something, the number of moles stays the same. It just gets more dilute, that's all. So as long as the number of moles don't change in here, our titration won't change either. So it's moles. There's my phenolphthalein. Phenolphthalein. 2 drops is really all you need. 1, 2, oop, 3. That doesn't matter. If you happen to put 3 in there, it makes no difference. And just swirl it around. So notice the color is completely clear because this is an acidic solution. And the color of phenolphthalein doesn't change until around what pH does it take for phenolphthalein to change to pink? Who was paying attention? What pH was it?
7.9.
Little higher than that. You say 7.9?
Yeah.
Little higher than that. It's around 9. It changes around 9. So it's a good indicator for our reaction because the pH at the equivalence point is going to be like around 8.8 or so. So that's pretty much exactly what we want. So we put sodium hydroxide in here. I think it's in a squeeze. You get it in a squeeze bottle. So you got to squeeze this for a good long time to get enough sodium hydroxide in here. And then just draw it up. If you don't have exactly 10 mils, it does not matter. So the volume is going to be the top of the syringe. Okay, that's going to be your initial volume. So the top of the syringe, not the bottom. So that ring, that top ring, that's going to be the volume, your initial volume. So my initial volume is like, well, that's actually right on 10. So 10 mils. Now, do not just put your thumb there and just blast away. You want to just sort of gently push from here, not from here, to add your 1/2 mil at a time. So notice when you put, so see how when you put the base in there, well, it's kind of hard to see. I should have a card up against it. I'll try that again. So notice you get this little pink color where the drops were. And then when you swirl it, it goes away. So that's what you want. You want the color to go away. It was just a couple of swirls. Get a pink color, swirl it, goes away. Now, if you get any acid or any base on the side, just swirl that some more. I think a blue color, what the hell is that? So you see it's getting a little bit darker, but still not pink, I would say. Yeah, you'll notice as you get further and further along. Did anyone notice that the more base you use, the longer it takes to disappear when you swirl it? That's what you're looking for. Yeah, because so if you just gently push from the base of the plunger, you can just add small drops at a time.
So what we're looking for is that pale pink color, right? To stay.
Very pale. Yeah, very pale. And if any of you have figured out what the concentration of acetic acid is already, based on what the 5%, you should pretty much know how much sodium hydroxide to add.
Professor, I have a question for
Yep.
that number 7 from activity 1.
Mhm.
It says transfer approximately 10 milliliters of 1 m sodium hydroxide
1 m, what does that mean?
molar.
Yep.
But how would you go about? Is it this one, or do I have the wrong
What does it say on it?
sodium hydroxide?
That's it. One molar, right? Yeah, you just gotta squeeze it.
I mean,
Squeeze it out. Yeah.
would that still work with this?
Yeah.
Yeah.
No. You squeeze it into a cup like that, and then use this to fill your syringe. You pull up the syringe.
Oh, okay, I got you.
Yeah. Yeah, don't rush. You don't want to rush it because I'm getting super close here. I just want to go drop by drop at this point. Add a drop, swirl it around. Yeah, I can tell I'm close because it's taking longer and longer for the color to go away. Man, that is close. Yeah, if it takes you 10 minutes to do one, that's fine. Because you definitely want to go drop by drop. Get super close. It should get a little paler color. There we go. It's a little more white. Yeah, I had a really hard ass analytical chemistry professor when I was an undergraduate. And we were doing titrations. And I said, I think I went half a drop over. And he said, well, you should have used quarter drops then, shouldn't you? So yeah, he was a real kindly guy. But I've been more careful with my titrations ever since that. Yeah, so now it's taking like 4 or 5 swirls to get rid of the color. So I know that probably 2 to 3 more drops and I'll have it. And you might actually get a purple. I'm getting a slightly purple color for some reason rather than pink. So maybe I didn't wash out my. Yeah, come on. Man, I can't believe the color's going back.
So mine did what you said it would, because it was doing drop by drop, and then all of a sudden it was one drop, and then it just like boom, color.
There you go.
Yeah, but it's dark though is the thing. So I don't know what happened.
How many drops of indicator did you use?
Just one.
Just one. Wow.
Yeah. Like I literally have been sitting here doing like pressing one time, letting it drop, swirl. So I don't know if maybe like more snuck in that last drop because I wasn't seeing anything for the longest time.
Yeah, I mean, it's going to be, like I said, it's going to be practically impossible to get it that light pink I showed you. And that was with a burette.
Okay. Well, I mean, we'll see what happens in the
Man,
second
this was-
sample.
I think it would appear I should have washed out my, because now I have blue. So I have a blue color. So there was something, quite obviously, there was something else in here that I did not wash away. So it went from clear to blue. So I think I will dump that out and wash it out again. Because blue is not really the color we're going for. Yeah, basically, if it changes with one drop, that's good. Even if it looks dark, if that's from one drop. It's really blue. I'm going to try that again. Hopefully it won't turn blue this time.
Professor, same thing
Mhm.
happened with me. Just one drop and then it suddenly
There you go.
it's too dark though. Not the light pink.
Let me see.
Yeah, that's what mine look like.
Right? It's just
Yeah.
one drop. It's
Because
just,
I was like, oh no, I did this wrong.
No. If it takes one drop, then that's what it takes.
I want that light pink color though.
It's pretty, right? It's a pretty color. I think I'm using the old phenolphthalein from last term. I'm not sure how stable this is over time. Though I've used stuff that was years old. So
Oh shit, I gotta tear first.
1, 2, there we go. Okay. All right. Let's try that again. All right, looks better already. I'm not getting any blue or green color. Yeah, so let that be a lesson. Make sure you've washed out the flask. I obviously had something in there. Yeah, now my color is disappearing completely. Before it was just staying pink. So this should work much better.
I think I had vinegar that touched the side of the syringe, and now my sodium hydroxide turned a slightly pink, which is the color we wanted.
Well, that's the indicator. That's not the vinegar doing that.
Well, yeah. So is that okay to use it still, or should I clean it out completely?
Hmm.
I think I have enough still. I
So-
mean, there's a lot in this bottle.
Yeah, I would just probably, yeah, you don't want any indicator on there. There we go. So is that working, Luigi? Are you getting drops out of the bottom? It's working all right? Oh, cool. Okay. Man, detention. I can't handle it.
What are we using for vinegar sample 2 and 3 again?
Whatever. Oh, same one. So you use this, basically we're doing these in triplicate. And then you get a new sample and do that one in triplicate as well. So the second titration, you can go a little bit faster since you pretty much kind of know what the volume should be. But the first one should take you the longest time. There, oh, it's so close. Here's where my old professor would tell me to add a quarter of a drop. Oh man, I see what you mean. Yeah. Yeah, that's one drop. So you're right. That well, I think part of the problem is that these syringes, you get pretty big drops. So yeah, man, mine is super. Now it's purple. Obviously, I didn't clean out whatever the hell was in there. But read my volume. 5, right on the nose. Okay. All right, I'm going to start working on my calculations. All right, so I'm going to start working on doing some calculations here. All right. So I had 5.95 grams of acetic acid. And you'll notice, I don't know, maybe you haven't noticed, but we use a lot of shorthand for acids. We typically put like HCl is written like that. There's the proton that gets donated, you know, HBr is written like that, and that's the proton that gets donated. Well, for weak acids like acetic acid, we pretty much use the same convention. We just use the shorthand AC for acetate and just write this. So there's the proton, and this is the acetate part. So you may or may not have seen people using that. Anyway, this is my mass of acetic acid. Now I want to turn that into a volume, but to do that, I need to know the density. And so my density is written in the right in the table, right in data, excuse me, right in data table number 1. And the density is, oops. It's 1.005 grams per mil. Now remember, we want mils, not grams. We want a volume out of this. So my grams cancel and I'm left with mils. So how many mils did that actually, was that actually? 5.95 divided by 1.005. So it was actually 5.92 mils. So now I compare that to my volume of sodium hydroxide. So my initial volume was 10.0 mils, and my final was 5.0 mils. So I delivered 5.0 mils, 1 molar. Oops, sorry, 1 molar. Oops. .0 molar sodium hydroxide. So I want to figure out how many moles sodium hydroxide I have delivered. So 5.0 mils times 1 liter over 1,000 mils times 1 mole for every liter. That's my concentration, 1 molar. Mils, liters, left with moles. So it's 5 divided by 1,000, or 0.0050 moles. So that tells me how many moles of base, how many moles of hydroxide ion I have delivered. And since I know from the balanced equation that 1 mole of acid is 1 mole equals 1 mole of base, then I know I have that same number of moles of acetic acid. So then I continue. So I had 5.92 mils of acetic acid, and I had 0.0050 moles. Now remember, I want to convert that into moles over liters. So I take the moles and I want liters, moles over liters. So that's 1,000 mils over 1 liter. One over 5.92 mils. So my mils are gone, and I'm left with moles divided by liters, which is the units I want. 0.05 times 1,000 divided by 5.92. And I come up with 0. Oops, it got erased. .845 molar. Now remember, we want to round that. I'm not going to round that yet, because there's still some calculations I need to do. But my initial concentration of acetic acid in the vinegar is 0.845 molar. That's too many significant digits for our concentration of base. Our sodium hydroxide only had 2 significant digits. So I will round that to 0.85 later. But for right now, I also want to figure out what is the amount of acetic acid in terms of percent mass. How are we going to do that? Well, I have 0.845 moles of acetic acid per liter of vinegar. That's what that means, right? So I want to do 2 things. I need to convert my liters to a mass, because basically I want the mass, the percent mass is equal to the mass of the acetic acid in grams divided by the mass of the solution in grams times 100. Remember, that's what percent mass means. The mass of my solute, in this instance, my solute is acetic acid, over the mass of the entire solution. So I need to know what the mass of that many moles. So my mass of acetic acid in 1 liter. So my mass of acetic acid, I need to convert moles of acetic acid to grams. Well, that's easy enough to do. How do we do that? How do we convert moles of acetic acid to grams?
Molar mass.
The molar mass. Exactly. So I believe the molar mass was 60.06. Let me double check on that. And that information was here somewhere. So I can just look it up. This is so strange. I thought for sure the molar mass was in here.
60.052.
Oh, I was pretty close. Thank you. All right. So 60.0, I should 052. All right, I was off by 100th of a gram. Sue me. Over 1 mole. And so that gives me 0.845 times 60.052. So that gives me 50.74 grams of acetic acid in a liter. So remember that if this was water, what's the mass of a liter of water? How much would 1,000 milliliters of water weigh? How much does 1 milliliter of water weigh? What's the mass of 1 mil of water? Or in other words, what's the density of water?
1
1 what?
grams.
1
Grams per ml.
1 grams, right. 1 gram per ml. But this isn't water, is it? It isn't. It's a solution. So I can't convert my 1 liter directly to 1,000 grams based on the density of water. What I need is the actual density of the solution. And luckily, we were given that. So 1 liter times 1,000 mils per liter times 1.005 grams per mil. That was the density. Remember, that was the density of vinegar that was given to you at the beginning. So that equals 1,005 grams. So I'm going to take out the 1 liter of solution and replace it with 1,005 grams. So this is my density of acetic acid in a liter. And I figured that out from the molarity. Remember, once you have the molarity, that tells you moles per liter. Well, just convert that to grams per liter. There's no point going back to like 10 mils or whatever the original volume was. Make it easier on yourself. If I have moles per liter, just turn it into grams per liter. So that was equivalent to that many grams of acetic acid in 1 liter. And then we just use the density This is the density of vinegar, because we're not dealing with water, we're dealing with a solution. And so we figured out that that is the mass of the entire solution. So now I just need to divide those two, multiply by 100. And that gives me my percent mass of acetic acid. So 50.74 by 1,005. So that gives me 5.05%. So remember, we need two significant digits because we have two significant digits in our concentration. So we're basically limited to two significant digits. So I would round this to 5.1. And let me double check. What does it say on the label?
5% acidity.
5% acidity. So what that means is that 5% by mass, not by volume. 5% by mass is acetic acid, and I got 5.1. So you should be able to get this pretty close. Yeah, so don't worry if the solution looks a little darker than we thought it was going to. That's not a. I think that I'm absolutely, well, now I'm absolutely certain that's because our volumes are so small that, you know, it's going to be an intense color. So as long as the color you see is because of one additional drop, and there's really nothing you can do about that. I mean, you could dilute the sample and get but the only point that would do is just like give you a more dilute color. It wouldn't give you any more accurate determinations. In fact, it might be worse because then you wouldn't notice the really subtle one drop change if you had a more dilute sample. All right, so should we review? So you're going to do this for, so that was just for one determination. So you're going to do 3 and get an average. So that's for this sample. And then you're going to use your own, whatever it is. And then finally, the third table, let's have a look at that. Okay. So let's look and see how you do the work for this one. So remember that this isn't from your particular experiment. It's from an experiment someone else did, and you're using their numbers. So the volume of vinegar used, is, wait a minute, why isn't this working? Oh, wait a minute. It's sharing the wrong thing. Okay, see if I can draw on this one. Hmm. That is, oh. What is happening here? Wow, this is weird. Okay, this looks like it's going to work. Weird. Okay. So the original volume of vinegar is 21.05 mils. So that's how much we start with. And it gives you what so from the burette, which was the instrument I showed you before, the long skinny tube, and it goes, unlike most things we measure with, it actually has 0 at the top and 50 at the bottom because it's dispensing. So we're looking at the amount of volume it's dispensing rather than holding. So that's the initial reading. That's the final reading. And so the amount of sodium hydroxide it would have dispensed is the difference. So 20.12 divided by 2.89. So it would have dispensed, let's see if I can write this a little smaller. .23 mils. So then we would calculate what the molarity of the acetic acid is, and that's using, all right, this is 0.1 molar NaOH. So I have 17.23 mils, and I've dispensed 0.1 molar NaOH. So not the 1 molar we were using. So you need a lot more of the solution. So we figure out how many moles that is. .23 divided by 1,000. That gives us 1,723 liters times 0.1 moles per liter. So we get a total amount of acetic acid in that sample of 0.001723 moles. And then that is the number of moles of acetic acid. That is the volume. And so we just calculate the molarity. So our molarity is 0.0819 molar. And you're probably fine with just rounding that to two digits. Even though they only give you one here, I would probably just use 2. So that would be the molarity of acetic acid in the sample. Actually, since you're doing more calculations with it, I would just use this for right now. So 0.0819 molar. Oh, it looks beautiful. Zero point 0.819 molar. So the volume of sodium hydroxide dispensed at the midpoint is basically halfway in between three. Actually tells you right here, the midpoint Burette reading. So at the midpoint, it is dispensed 12.92 minus 3. So that's 9.92 mils of 0.1 molar sodium hydroxide. So that's the volume, 9.92. So what you want to do is then, what's the volume dispensed at the midpoint? 9.92 mils. What are the moles of sodium hydroxide consumed at the midpoint? So that would be 9.92 times 0.1 molar sodium hydroxide. So figure out number of moles of sodium hydroxide. That's the number of moles of sodium hydroxide that would have been consumed. Now, you figure out what, from the concentration of that you figured out already, 0.0819 molar, how much of the acetic acid would be remaining. And you do that by figuring out how many moles of acetic acid were there at the beginning. You subtract the number of moles of the conjugate base, and that gives you the amount of acetic acid. And then you just use the formula that was given. Use the formula that was given, the Henderson-Hasselbalch equation, which is pH equals pKa plus log conjugate base over acid. So figure out what the concentration, the molar concentration of the conjugate base. You've got that from here using this volume. Actually, the 9, what's my volume? Midpoint was 9, right? 9.92 mils. So that's your volume at the midpoint. That's the number of logs of A minus at the midpoint. Number of moles. Ugh. So figure out what the concentration of the conjugate base is. Whatever is remaining from your initial concentration, that's the number of moles of acetic acid. Figure out what that is. It gives you what the pH at the midpoint was. The pH at the midpoint was 4.895. And so A minus, the concentration of A minus and HA should be pretty similar. Should be pretty close. Not exactly the same, but pretty close. And so this term should be pretty small. And your pKa should be fairly close to 4.895. Any questions on how to do? I know I went through this rather quickly. You want to try it again? Everyone's actually doing their titration, so. All right, I'll go through one more time. Actually, I'll put a little more screen. Let's write this information down. All right. Just look at this right from the beginning. So they give you a volume at the midpoint of the titration. And so the volume of the midpoint of the titration was 9.92 mils. So that's how much sodium, 0.1 molar sodium hydroxide was dispensed at the midpoint. So we need to figure out how many moles that is. So 9.92 mils times 1 liter over 1,000 mils times 0.1 moles per liter. Oops, 2 divided by 1,000. So that is 0.000992 moles of OH. Now remember, when we are titrating a weak acid, basically what we're doing is we're converting the strong base into conjugate base. So that's going to be the same number of moles as my acetate ion. Acetate minus. So same answer. So this is the number of moles of sodium hydroxide that are consumed. Well, what happens to them? They get converted to acetate because this is the reaction. OH minus plus acetic acid gives you water, acetate. So that's what happens to the hydroxide. It peels off the proton from acetic acid and makes water and then leaves us acetate. So the concentration of this should equal the concentration of this, as long as both are less than the concentration of acetic acid. once the acetic acid runs out, then it's basically gone, and we've converted all of it to this. But until that happens, my concentration of base should be the same as the concentration of acetate ion. So what is that constant? Let's figure out how many moles of acetic acid we had at the beginning. So I think, where is, oh, here we go. We calculated how many moles of acetic acid we had at the beginning. To do that, we use the concentration. I think the concentration was around, looked like it was dilute. It was like 0.0885 or something like that. So that was the concentration. So it seems to be like 10-fold less concentrated than the acetic acid we're using. So we want to see how many moles that is. So remember, the volume at the beginning was it 20, 21? Let's say it was 21 mils. It was something like that. So 21 mils times 1 liter is 1,000 mils times 0.0885 moles per liter. That gives us moles of acetic acid at the beginning. That gives us 0.01859. Remember, you don't need to round until we get to the end. So that gives us this many moles of acetic acid at the beginning. And at the midpoint, this is how many moles of hydroxide and moles of acetate ion have been produced. So we need to know how many moles of acetic acid are left. And so we just subtract. Takes me a while to erase all this stuff.
Professor, I got a different answer when I multiplied 21 to the 0.0885 mole over 1,000.
Okay, let me try that again. So 21. 0.085. Oh, 2 zeros, right? 2 zeros.
Yes.
Yep. See, it's really easy to make a mistake of a factor of 10. I mean, biologists do that all the time, but chemists shouldn't do that. Okay. So my difference is So my difference is 0.0008665. 8665 moles. So that's how many moles of acetic acid I have left. This is the number of moles of acetate I've got. So basically, we're looking at pH is equal to the pKa plus log. And you can convert both of these to concentration, but it really doesn't matter because we're looking at the ratio. We're looking at the ratio of these two things. So if you convert them both to a molarity, it doesn't affect the ratio between them. So you can go ahead and do that, but it doesn't really matter. And I think it's A minus over HA, right? That's the correct formula. I want to make sure I don't. I think it's the acetate on top and the acetic acid on the bottom. Is that correct? Someone want to check for me?
Correct.
Okay, good. So that is, and what's the pH at the midpoint?
4.895.
4.895 equals the pKa plus the log of that ratio, which should be pretty close to 1. 8.664. Yeah, pretty close. So the log of 0.8735. So if someone can get the log 10 of 0.8735, it'll be pretty close to 0. It'll be a really small number. So we've got a scientific calculator, knows how to use it.
Wait, so was log 10 the same as the negative log? I'm just
No,
trying to stick with
No, it's just log. You just don't want the
Log, right?
natural log.
Because I got a negative number.
Okay, that's fine.
Let me try again though.
Yeah, it should be negative. It should be small and negative because the log of 1 is 0.
Got negative 0.0587.
0.0587. Okay. So all we do is add 0.0587 to both sides. And that's our pKa. So 4.895 plus 0.0587. So it gives us a pKa of 4.95. Like I said, it's going to be pretty close. However you calculate the number of moles of acetic acid and the number of moles of acetate midway through, that ratio is going to be really close to 1. So either you're going to add a little bit to the pH at the midpoint, or you're going to subtract a little bit from it, but it's not going to change that much. So you shouldn't get a substantially different number than like 4.9, which is actually the pKa of acetic acid.
Wait, so you got 4.895?
I got 4.95. 4.895 is the pH, because remember, the pH is equal to the pKa times this ratio. So this ratio is going to be approximately 1, so that the log of something close to 1 is going to be a really small number, slightly negative or slightly positive.
But you said you just added 4.895 plus negative 0.0587.
Right, so I added, so this was my pH. And if I add that number to both sides, I get rid of this expression, and all I'm left with is pKa equals the initial pH plus this little difference here.
Okay, because I got 4.836, so 4.84.
Oh, did you subtracted it?
Oh, so we add it. So we
You need to
turn
add
it
it.
into a positive.
You need to add it.
Oh, okay, okay.
Yeah, because remember, you're subtracting this number from the pKa and getting that number. So the pKa has to be larger because you're subtracting this from it to get the pH. You have pKa plus a negative number equals the pH. So the pKa has to be larger than the pH. You have to add that little bit.
Okay, that makes sense.
Yeah.
Okay.
Oh, it does? Good. Because it's barely making sense to me anymore.
Well,
I have to say it's getting late.
I think it's just that the negative integer is just what threw me off.
Mm-hmm. Yeah. Yeah, if you get a positive integer, you get a negative integer, it doesn't really matter. It's going to be small. It's going to be really close to zero. So don't worry if it's a little negative, it's a little positive. Do worry if you get something like 2 or -2 or something like that. Then something's screwed up. Because that ratio of conjugate base and acetic acid should be pretty close to 1. Because that's the whole point of being the midpoint. You have converted approximately half of the acetic acid to acetate ion. That's what should happen at the midpoint. Right, let me do a quick check. Oh dear, 2 to 1, top of the 9th. Of course, everyone probably knows that already. I won't mention that the Dodgers were my late father's favorite team, but I'll just leave it at that. Anyway, he'll be happy, but still got the bottom of the 9th coming. See what we got coming up. Oh dear, yeah, 2 outs and 2 on, so this is kind of important. So has everyone found a second vinegar? Oh, Chris, how did your the sushi seasoning work? Were you able to see the color change?
I actually got it pretty well on the very last attempt. I did like micro drops and I got like a pretty, I think one more drop would actually turn it to purple. It's really
You're getting
close.
a purple color rather than a pink color. Yeah, it's interesting.
Yeah.
Like, so that's what I got my first time too. But of course, there's a bunch of other stuff in there, right?
Yeah,
There's a bunch of sugar in there.
there's a
and,
bunch
like,
of sugar.
sugar reacts with hydroxide too.
It's like 2 different vinegars in here.
So do you have any idea what the concentration of the 2 different vinegars in it are? So you can like, compare it, your result to it? Do they give you a recipe breakdown?
No, not really. I have to look it up.
Okay, that's cool. But
I
yeah,
was gonna ask about that.
it's a commercial product then.
I use it's like Filipino vinegar. So
What's it
it's
made
like
of?
cane vinegar and water.
Okay,
So when I did the first 2, it was like bright pink, but then for some reason, the third one, I don't know if I just was going much slower. I actually got the light pink color. I took a
Nice.
picture of it. Yeah,
So
so
what does it say what the acidity of it is?
4.5% natural acidity. That's all it says on there. And then the
Oh, so it should
ingredients
be
is
pretty
just
pretty
cane
close to
vinegar and
the.
water. Yeah, but I mean, the first two look just like the last set.
Mhm.
And then that third one, I don't know what I did that was different, to be quite honest. But I
You managed
caught
to get that quarter drop.
yeah, I caught the light pink color that we were
Nice,
looking for
excellent.
on the third one.
So what makes the Filipino vinegar any different, do you think? Is it just, it's just a brand name? It's not, it's
I
still,
honestly
it's
don't
still just
know.
acetic acid, right?
I mean, I wouldn't use regular vinegar to eat with my food, like the distilled white vinegar. I don't know. I think it tastes differently.
Is there like any sugar or anything else in it?
Well, it's cane sugar that's in it. So I don't know. I feel like the taste is a little bit different.
Okay, cool. Yeah, I mean, I'm trying to think. I don't think that should affect. I don't think there's going to be.
I mean, the
a
acidity was about the
reaction.
same because this one says 5% acidity. The
Mhm.
other one was just 4.5. So
Yeah,
I didn't think it was
I
gonna
don't
make a
think the
difference.
sugar is going to affect anything.
I think you're right. I think it was just for what somehow I was able to get just like that tiny, tiny bit
Yeah,
instead of like that full drop just came out.
it's really hard to do because yeah, these, we're dealing with sort of like a brute force instrument here. With that burette, you're able to make really small drops. With a syringe, it's kind of difficult.
Yeah, a little bit would get stuck. And I think that's what it was with the last is you would put a drop, but another drop would literally be at the edge.
Exactly.
And it sometimes it would fall and sometimes it wouldn't. So
Mhm. Yeah. Yeah, I mean, that's, I think, like two significant digits is like the most we're going to get out of something using the equipment we're using and the solutions we're using. So if you get close to like 5%, excellent job. I'm really curious to see if the vinegars with other stuff in it are affected, or whether you get the same result. Pretty sure you should get the same result. Wait a minute. Nope, they got out of it. So Crawford, Bryant, and Slater coming up next. Let's hopefully Crawford can get on. Doesn't try and play hero.
I bet your Wednesday night lab is happy they didn't have class.
Well, they're all freaked out because they thought I was going to make them all come in tonight. But eventually, I mean, you guys will get a week off, and then because they're going to do this lab next week.
So for us, what would be our lab for next week?
I haven't decided yet. I think I need to look. It'll either be the buffer. There's a buffer one. And there's one with just looking at reactions, different types of reactions. I need to look and see which one.
I was just wondering because next week is the one that I'm flying out and there was no way I could make it to either day. With those labs, I know because I always, if I miss, I figure I can watch the video, but is it something that we could do independently ahead of time, or do you prefer that?
I'll check. Because yeah, one involves like fire and stuff. So I
Yeah,
wouldn't
because
mind
if it's
doing that one.
straightforward, I'm just wondering if I can get a head start.
But I think the one with the buffer is probably do that one because it's related to the acids and bases still, and you actually be measuring pH with paper. So I think that one's going to be pretty straightforward and relatively non-toxic. All right, does anybody have any questions, like especially concerning the calculations for table 3? There's a lot of calculations to do. Hopefully I didn't make it too confusing. Is everyone finished their titrations already? It's like a lot of you have, right? Now it's just calculation time. Ricky, you still doing some titrations?
No, I just finished a few minutes
Okay.
ago. Just doing some calculations now.
Still looks like you're spinning some house music or something. Some old style drum and bass. All right, I'm gonna hang, so I'll hang for another like 5 minutes or so, if anyone has any questions.
I started at like 6 mils, I think, for the second one,
Okay.
because I was trying to like gauge like how much I would have left over.
So went to 6, then
So-
down to 2.
Yeah,
Oh, okay.
I don't know. I'll check it again, but I'm just wondering if that made a difference.
It shouldn't. I mean, you should pretty much get the same thing each time. That's odd. You don't
I
think there was
probably
like an
didn't
air
measure
bubble maybe in
exactly.
the first?
Yeah, well, maybe because like I said, like when you first start using the syringe, because there's
Yeah, it sticks, right?
yeah.
Yeah, it could just be an air bubble or something. Yeah, I mean, that's, your results are your results. I mean, it'll be fine. I mean, basically, we just want to be able to see like, can we perform the titration fairly well, and then can we do the calculations, and then can we make sense out of our results. So it sounds like you got 2 that were the same and 1 that was different. So I don't know, I think the average of them will probably be fine. Because you should, what was the volume of acetic acid you wound up with? Was it around 5?
I haven't gotten that far yet.
What was the mass of the acetic acid?
Of like how much I put of
Yeah.
the vinegar that we started with.
Mm-hmm.
It was for the first one, it was 5.07 grams.
Okay.
And then the second one was 5 grams. And then the third was like 4.74 grams.
Okay.
So
Yeah,
they were
so
all still within the same range, I guess.
So you should get somewhere between 4 and should be like around 4.5 mils for that. So I mean, your average is going to be pretty much perfect, I think. So yeah, you're like, a little off on one side and then a little off on the other side. But I think that's what happens when you do experiments, you get variation. And you hope that when you do the average of it, those variations will even out. That's what we learned last week, right? That we get variations above, we get variations below. But if you average enough results, you're going to get a pretty good number.
Professor, I think this is a good color, right?
Oh, that's perfect.
Yeah.
Yeah, that's really nice.
On
Yeah,
my
that's
third
excellent.
try.
Yeah, use that for your picture, because it's just not going to get much better than that.
So just one picture for
Yeah.
each.
Yeah,
Okay.
yeah. I would definitely use that one, because that one's perfect. Yeah, I would say you got your quarter drop on that one. Because I
didn't look
noticed,
at
I mean, I saw the same thing you guys did. I mean, with one additional drop, boom, it got like really, really dark. So
I didn't look
presumably,
at the final one, like the final like draft that we have to do, but is it just one photo for each?
yeah.
Like, okay.
I think so. I'm pretty sure. Yeah, I'm pretty sure it is. I can double check, but I'm pretty sure it is.
The template just says 2 pictures total.
Yep. Mm-hmm. Yep. After the addition of phenolphthalein, and then at the endpoint. Yep. So yeah, so if you've got an excellent endpoint, like Eva, yeah, use that one.